this next section, we're going to talk about reductive amination. It's a way to synthesize amines. So the first reaction here involves an amine. So here we have an amine, we have an aldehyde or ketone, right, and also H plus present. And what you make as you go through and do that, if you recall, is you end up making your R carbon, R prime, double bond nitrogen here. And that's your Z group. So that's your step one that's happening there, right? So we remember seeing that. So it could be this, and that's either an H, so it's either an amine, or sometimes we see it as an oxime here. This could be an oxime also. So that's your step one, and then step two is your reduction. Right, so that reduction can be done using LAH, so often we just use LAH here. It's like the go-to thing that we've used this semester. But we could also use catalytic hydrogenation, so H2 nickel, or we could use HCl and zinc or tin. So there's a lot of options actually out there, but I think students prefer just to use this since it's kind of the go-to chemical to use for reduction. And it works for all, but aminium ions are aminium salts. So we'll talk about that on the next page here. So it works for all the cases except for aminium ions. Now, let's take a look at the reaction down here below. A lot of these mechanisms we've already discussed, so we're not going to go over them again in detail. But here we can take a ketone or an aldehyde, and we can add NH3 here. That would make the imine, but in lieu of that, we often use NH2OH, hydroxylamine. And we do that because it's just less volatile. Ammonia, if you've worked with it before, it has a very strong odor. It's just a little bit tougher to work with. In any case, we get the oxime, and then we do a reduction to get a primary amine. So one way that we could do this, if we're thinking about multi-step synthesis, for example, is you could take 2-butanone, right, treat it with the hydroxylamine, add some H plus in there, right? You're going to get your oxime here, right? And then we do a reduction with LAH and H2O, and in this case, it gives us a mixture of enantiomers. Now, if we want to get a secondary amine, what we have to do is we have to start off with one R group on our nitrogen. So it's the same deal where we have our aldehyde or ketone here, and you add your amine here and H plus. So same general conditions as we saw up above. The only difference here is that you have this R prime prime here. All right, that makes the imine. There's your R double prime, and then you do a reduction, and that gives you your secondary amine. Sometimes students are interested in knowing what the mechanism for that reduction is. Well, it's actually pretty straightforward. So remember, we're using lots of different things, but if we're using LAH, then that's a source of H minus, right? So our H minus would come around and attack our carbon, putting our electrons up onto nitrogen. So that would have 2 lone pair there. And then our second step here, right? So remember, it's 1 LAH, right? And then 2, you do your workup. So that puts the H on there. Again, we talked about this before, but different chemicals can be used to achieve that reduction. But most students tend to lean towards just remembering this since it's just so commonly used. Now, what about tertiary? So we talked about primary and secondary. But tertiary amines are not stable usually. They're typically pretty unstable. So the way that we make an aminium ion is that we take an aldehyde or a ketone here, and we add an amine that has 2 R groups with H+. All right, we'll talk about what this thing is in just a moment. That makes the iminium ion, or the iminium salt here, and that is typically unstable. So just make a note here that we're generally unstable here. Okay? So what happens is that these want to quickly form the enamine, but what we'd like to do is reduce this, and we have to do that within the course of this reaction taking place. So that means that we need to add into this original mixture over here something that will do a reduction but not be overly reactive with other reagents. So we're going to use a weakened form of NABH4. So we're going to take off 3 of the H's and put a triacetoxy group there. So that's the one that our book commonly uses. So that's sodium triacetoxy borohydride. Another one that you're going to see there is sodium cyanoborohydride. But that's included as part of the reaction mixture. So all that stuff just goes together, and the reduction takes place once that iminium ion is formed, and that's where you have your tertiary amine being formed. So the only difference in that mechanism is that you just have to remember that that the NaOAC3BH is going to be added in the course of the reaction. Now, what we usually see as far as our reaction arrow goes is in predicting products is you'll see like an R2 NH, H+, and then the sodium triacetoxy borohydride, so Na, right, OAC3 BH. So that's what you see typically above your arrow when you're trying to predict products. Now, a couple other reactions to finish up with here. Some of these are going to be covered in chapter 21. Like this next reaction here involves an amine, and we add to it an acid chloride. So we're adding these 2 things together, and then that forms an amide. Remember, an amide is this carbon, double bond oxygen, nitrogen group there, right? That's your amide. And then we do a reduction to get our amine here. So the interesting thing to point out here is that bond, and you probably already know this, but this is a new carbon-nitrogen bond here. All right, so what about reduction of nitro compounds? So we've seen some examples of that before, or we've seen reduction before of carbonyls with the Clemmensen reduction. So it turns out that Clemmensen can work on nitro groups to some extent too, although our book uses a different reagent. So kind of the process of reacting here is this, is that you take a benzene, you add HNO3, H2SO4, right? So remember, that's an EAS reaction. That'll put a nitro group on our ring. And then what we want to do is we want to do a reduction. So we can use a couple of reagents. So your book uses H2 with some type of a metal catalyst. So it'll be nickel, palladium, or platinum. Or they use H+, so a source of H+, like HCl, for example, with another metal. So you see iron here, zinc, or tin. So I think students typically like to use this, HCl and zinc, because it's reminiscent of Clemmensen reduction. All right, so when we do that reaction, especially if we do this one that's listed in red, so I'll write our product here in red. If you use those reagents because you're in the presence of H+, you'd form NH3+ there. And then you would have to use some type of a base to do a deprotonation there And then that would give you your NH2. So you get your amine in there. All right, so let's talk about azides here. So there's reduction of azides. It's an interesting reaction. So it turns out that azide is an inhibitor of F1 ATP synthase, just as a side note. But azide ion, let's talk about what that ion is. So it's easy for us to forget what the Lewis structure of this is. So let's take a look here at our Lewis structure. So the Lewis structure is 3 nitrogens stuck together with 2 double bonds. So right off the bat, that's going to put a plus charge here. And then we're going to have at each end a set of lone pairs. Right, 2 of them actually, and that gives you this. So that's where your N3 minus comes from. So it's a nucleophile. And if we look at this example down below, we can make some sense out of the reaction. It's pretty predictable. So let's take a look at, how about CH3, CH2, again, here, just a leaving group. So that could be a tosselet, it could be other things too. Now to this we will add azide, N3 minus. So let's draw out that structure here again. Put in your formal charges and your lone pairs. And what's going to happen here is we are going to get an SN2 reaction. So SN2, we're coming over here to that carbon, kicking off electrons to the bromine atom, okay? All right, now that's going to give us CH3, CH2, and then we'll be connected to the azide thing, right? So then we have our nitrogen here, double bond, nitrogen, double bond, nitrogen, negative charge, positive charge, lone pair here. So the way that we're going to start our resonance is at the end of the molecule at the nitrogen atom. So we're going to start off here, we're going to do this. Okay. Now we can't leave it like that because nitrogen would have too many bonds, that middle nitrogen. So we're going to come over and we're going to do that. So that's our electron flow here. That's going to give us CH3, CH2, and then our nitrogen here in the middle is going to have a minus charge, right? And then we'll have our other nitrogen here, triple bonded to a nitrogen at the end, right? And that's going to give us a plus charge right here. Okay, so basically here what happens is we're going to end up getting this group. That's going to eventually leave as nitrogen gas. So the second part of this reaction mechanism, we're really not going to get into the details of that step, but what we would use here is typically LAH and H2O, or you could use catalytic reduction. So that's like H2 with palladium, for example. In the end, what you end up getting here is CH3, CH2, NH2, and then plus here nitrogen gas. So I use that arrow up to indicate that. Interesting side note is azide is very explosive. It's a great nucleophile, but it's very explosive too. It's used in some rocket fuels, and it's also used in propellants for airbags. So certain azides, in fact, can be explosive just on touching. So you have to be careful when you use azide. You have to be careful what solvents you use. If you use methylene chloride, for example, with azide, you can get diazomethane, which is an explosive chemical. So anyway, they just need to be treated with care. Azides also react with all sorts of other electrophiles other than alkyl halides. So we could react with epoxides, for example. So here's an epoxide Na(N3-), opening up. As we open that up, remember that N3 and the OH, right, or the oxygen that leaves, will be anti to each other. Right? So remember that's that three-membered ring principle. And then here we're doing a reduction. So H2, palladium, takes that down to an amine. So the last reaction that we're going to look at here in this chapter is the addition of nitriles to alkyl halides. So here we have a cyano group, or cyanide. So this is going to be an SN2 reaction. So if you remember back in chapter 6, we probably saw something like this back there. And that makes a nitrile here. And then we can do a reduction. That reduction often is done with LAH and H2O there. Notice that catalytic hydrogenation works too, but again, students tend to like to use LAH because it's just the go-to thing. But what happens here is that our carbon becomes a CH2, and our nitrogen there becomes an NH2, and that gives us an amine. Right, so if we look down below, sometimes you'll see reactions like this, and this helps us trace where the H's go from LAH, right, because you get a hydride there, and where the H's go from H2O. So this first step, pretty straightforward again, right, SN2 here. So that's our carbon triple bonded nitrogen, right? So this is our CH3, CH2, carbon, triple bonded nitrogen, if we wanted to draw that out. And then what's happening is that carbon right there, right, this guy right here, is getting H's from LAH. Okay? And then the nitrogen is getting its hydrogens from step 2. And remember, D just means deuterium. So what you need to remember here is that those protons are equivalent here, deuterium, they come from step number 2, right? In this case, D2O, right? Or commonly H2O, right? And then the H's that come on that carbon arrive from LAH. And then you could also use the deuterated form of that, would be LAD or LiAlD4. So sometimes you'll see questions like this come up where they swap around the reagents and ask you what the product is, and you need to make sure you know where the deuterium is going to go. Now there's one more reaction that I think is interesting biochemically, so I'd like to take a second and talk to you guys about that. And we're going to look at sulfa drugs. Sulfon amides. So there's a couple interesting things that happen here. So let's take a look at this reaction flow here. So we'll start off here with NH2. So aniline. And what we're going to do first here is we're going to protect this nitrogen. So we want to do an electrophilic aromatic substitution, but if we have anything in here that's slightly acidic, that'll get protonated, and that'll deactivate the ring. So what we're going to use here is this. We're going to use an acid chloride. Now what we get is our next product here is an amide. So we get our nitrogen, right, with an H connected to carbonyl and your R group here. Right, so essentially what we've done here is we've protected this nitrogen from being protonated as much, because that lone pair is tied up in resonance with a carbonyl that makes it less basic. So we have here an amide protecting group. Right? What we're going to do next here is we're going to add this. Okay. So what this is going to do is that's going to add to this position down here. It's going to be pair substituted. All right, now the mechanism of this we haven't really covered, but what the end result is that we get our sulfur here with our double bonded oxygens and a chloro group here. So now what we're going to do here is we're going to add NH3, and basically that's going to attack this sulfur, and we're going to kick off chlorine as a leaving group. That'll leave us with a plus charge here, so we'll do some type of a workup to get rid of that charge. But that'll give us this with our sulfur, and then down here and NH2. And then the last step that we're going to do is we are going to remove that protecting group. So it's a nice protecting group because it can be removed easily with dilute HCl and a little bit of heat, and then followed by a base workup. So you might use NaHCO3, for example. Now what that gives you is your benzene back with your NH2 and then your sulfur and your NH2 here. This is a sulfanilamide. So it turns out that this molecule kind of looks similar to PABA. And PABA is para-amino-benzoic acid. So here's your amino group, and here's your acid part. So they look similar to bacterial enzymes. So what happens is that when you have this sulfa drug in your system, bacteria that are in there take a look at what's available, and some of the times they're going to take that drug and they're going to use this right through, again, bacterial enzymes, and they're going to incorporate it into something called folic acid. So this red route gives us a folic acid that's not effective. It's not good. It's not normal folic acid. Folic acid is used for reproduction and cell growth. So with a bad form, or maybe an inactive form of folic acid, it slows bacterial growth so that your body has a chance to fight the infection. Right? So the normal PABA is incorporated into an active, right, or functional folic acid.